The atmosphere is made up of 5 layers which contain all the gases that protect us from the dangers of outer space. The lowest layer of the atmosphere is called the troposphere. This is where almost all weather occurs. The troposphere begins at the Earth's surface and extends to anywhere between 4 and 12 miles high. The varying height gives this layer more of an egg shape, with a height of about 4 miles at the poles and closer to 12 miles at the equator. In the troposphere, density decreases with height, meaning as you go up in altitude, the temperature decreases and the air becomes thinner. Just to give you an idea of the temperature change, by the time you reach the top of the troposphere or tropopause, the temperature will decrease to about minus 60 degrees Fahrenheit or minus 51 degrees Celsius. The stratosphere extends from the tropopause up to about 31 miles above the Earth's surface. In this layer, temperature increases with height due to the creation of ozone that's present in this layer. The increased temperatures make the stratosphere a very stable atmospheric layer and give thunderstorms their famous anvil-shaped tops. The next layer of the atmosphere is called the mesosphere. The mesosphere extends from 31 miles to 53 miles above the surface of the Earth. This layer is where most of the meteors burn up in the atmosphere. Temperatures once again decrease as altitude increases, similar to what happens in the troposphere. The thermosphere is next and extends from 53 miles up to 375 miles above the Earth. Being one of the outermost layers, the air here gets bombarded with ultraviolet and X-ray radiation from the sun, which, in turn, causes a large temperature increase, as high as 3,600 degrees Fahrenheit at the top. The last layer of the atmosphere is called the exosphere and is the outermost layer. It extends from the top of the thermosphere to 6,200 miles above the Earth. In this layer, atoms and molecules of the atmosphere escape into space. The atmosphere is important, but we need to also look at the big picture. Here is Earth. The sun heats the Earth, but it does not get heated evenly. At the equator, the sunlight is more direct and heats the surface the most. Out toward the poles, the sunlight is spread out over a larger area, so that area won't heat up as much. This creates an area of rising air at the equator, which in turn creates surface flow from the poles to the equator. This simplified circulation pattern is just a concept. The rotation of the Earth changes everything. The Coriolis force, a force created by the rotation of the Earth, causes the circulation of air to flow and break up into 3 distinct cells. In the northern hemisphere, the Coriolis force acts to turn the wind to the right. The circulation pattern is what gives rise to the westerly flow over much of the U.S. from 30 north latitude to 60 north latitude and the easterly flow from the equator to 30 north latitude. There are several other factors that can also affect the circulation of air. Things like seasonal changes, topography, and friction from objects on the surface. The Earth's circulation patterns always try to maintain a balance. This means that air flows from the areas of high pressure into areas of low pressure. This causes both horizontal movements of air, called wind, and vertical movements of ascending and descending air. In the northern hemisphere, a low-pressure system will have air circulating counterclockwise as it flows into the center. A high-pressure system will circulate clockwise as it flows away from the center.
This was one of the biggest volcanic explosions in history.
Daybreak and Mount Pinatubo burst angrily into life again.
It happened on June 15, 1991, in the northwest of the Philippines. It was so powerful, it produced a gas cloud that reached the stratosphere. The explosion caused a lot of damage locally, but the cloud itself did something extraordinary. It lowered the Earth's temperature for 4 years. Sulfur dioxide in the cloud created particles which spread around the Earth. These then reflected some of the sun's rays into space. Scientists are looking to mimic the effects of this phenomenon to counter global warming. It's a highly controversial concept known as solar geoengineering. Climate change is probably the biggest problem humanity faces today. In the past 25 years, the global average temperature has risen by around 0.5 degrees Celsius.
The accumulation of carbon in the atmosphere is warming the Earth up, making more intense hurricanes, rains, higher temperatures.
So far, governments have focused on policies for cutting emissions, but they keep rising. The concentration of carbon dioxide in the atmosphere has risen 15% since 1994. The Paris Agreement, signed by 175 parties in 2016, was a sign that countries were willing to work together to cut emissions. But not every world leader is on board.
The Paris Climate Accord is simply the latest example of Washington entering into an agreement that disadvantages the United States.
If emissions aren't reduced, what next?
Theoretically, solar geoengineering could cool the entire planet. It's actually potentially incredibly simple because all you need to do is inject a bunch of particles into the stratosphere, and there's a number of ways you could do that. Recently, a study out of Yale and Harvard looked at the details of how this would be done.
In that Harvard and Yale study, they imagined building a fleet of planes, up to 95 of them, that would make 60,000 flights a year. The fleet would spread hundreds of thousands of tons of sulfur dioxide into the stratosphere every year. After 15 years, they reckon the world would cool by 0.3 degrees Celsius. But there are reasons not to do this. One of the biggest concerns is that it could make governments complacent.
The big worry is that it will be exploited to argue against emissions cuts. Geoengineering is a supplement to cutting emissions, not a substitute for cutting emissions.
It would also be politically messy. If the plan is to put a thermostat on the Earth, deciding who has their hand on the dial won't be easy.
For it to have a global effect, you're going to need all governments on board, and that is going to be extremely difficult. If a country went alone and decided to do it on its own, then obviously because the impacts are going to be regional or global, you could create a lot of international tension.
A Swiss proposal to study geoengineering and how it should be regulated was recently put forward at the UN Environment Assembly. But America and Saudi Arabia opposed the motion, possibly because they don't want international regulation of geoengineering. As things stand, not enough is known about how it could impact the climate or the chemistry of the atmosphere. There could be unexpected consequences.
You can affect rain patterns, and you might cause a region that is already suffering from drought to have even less water. A lot more basic research, both into how we would do it, but also what the consequences of it would be if we did it in one way or in another way, is needed.
But of course, if we don't do it, there's deep uncertainty about how much climate change we get for a given amount of CO2 in the air. Both of those are risky, both are uncertain. The question is, which has higher risk?
The politics of solar geoengineering are so complex that it might never happen. That said, as the world continues to warm, the case for exploring radical measures grows stronger.
Even if we cut our CO2 emissions in half every decade, we will still have to remove several 100 million tons of CO2 from the atmosphere by the end of the century. So we have to ask ourselves where we can put it.
Norway has a lot of experience removing and storing CO2. Equinor extracts natural gas on a peninsula near Hammerfest, the northernmost city in Europe. Andreas Sandvik is in charge of the plant. He's proud that a way has been found here to get rid of CO2, but also to deliver an immense amount of fossil energy to Europe.
It is amazing. I mean, it's a lot of energy. So typically, energy for a city of 60,000 inhabitants for a whole year. And that's about 1.2 gigawatts. So it's amazing, huh?
CO2 is always a byproduct of natural gas extraction. But the crucial thing here is that it flows back under the North Sea. The system is controlled remotely from the command centre. There's no offshore platform. One pipeline brings natural gas to the plant, while another carries CO2 back under the sea.
In this, the gas stream coming in, about 6% of the content is CO2. And this is quite unique about this plant, because we remove the CO2, we dry it and compress it, and we push it back to a separate reservoir offshore, for permanent storage. So 90 tons an hour, almost 800 tons a year that we store permanently in a reservoir offshore. 143 kilometers out.
The state-owned company that made Norway one of the richest countries on Earth would like to benefit from this experience. Equinor is in the process of establishing a new business model. It calls the project Northern Lights. As early as 2023, the first ships will bring CO2 from European industry to Norway. A new pipeline descends steeply from the coast, then runs 110 kilometers along the sea floor to a point where the greenhouse gases are injected 2,500 meters deep into the North Sea's sediment. Sverre Aavara is responsible for the new field of business. It's his job to lead the company into the future.
Norway, it's seen as an opportunity to actually continue to use the resources that are in the North Sea, not as an energy provider, but as a storage provider for industrial CO2.
Construction of the plants has started and the first test drilling has been done. The gigantic Northern Lights project is meant to pave the way for the large-scale storage of CO2. Its initial goal is to free Europe's industries from greenhouse gases.
If we succeed, then we have the opportunity to actually help clean up quite a few of the industries that have no other option. And we will allow these industries actually to stay here in Europe. It's hard to see a world without steel. It's hard to see a future without cement. They are essential, and they need to decarbonize as well.
Even if steel production switches to renewable energy sources, there will always be an amount of CO2 left over from the manufacturing process. Looking at German industry as a whole, this remaining CO2 accounts for around 7% of CO2 emissions. If Europe is serious about climate protection, these emissions must also be stopped. But is it realistic that freighters will bring CO2 from Germany to Norway? Today there are only 4 ships like the Frøya worldwide. Tommy Pedersen is responsible for loading the tanker. In the Norwegian port of Porsgrunn, it takes on CO2 that was released during the production of fertilizers.
Down. Down.
The gas is delivered to the food industry, which uses it in beer and fizzy drinks, for example, or for cooling. Today, CO2 is a commodity in small quantities. After the gas has been cooled and compressed, the Frøya transports it in liquid form. The tank holds 1,500 tons of CO2. Assuming that all of the carbon dioxide produced by German industry would be transported by ships like the Frøya, around 100 of these tankers would have to travel from Germany to Norway every day. But that's not a problem for the specialist.
In theory, it will be just a cost calculation. How is the optimum size of the ship from, let's say, around the North Sea down into the Northern Sea seabed? So I'm sure that if this is a technology that those companies who are into this, they will just calculate the right size of the ship.
So shipping CO2 to Norway is plausible, but would those millions of tons of greenhouse gases really stay put under the ocean floor?
On an isolated mountaintop, they're doing what was once unthinkable. Taking water and transforming it into energy.
We generate more megawatt hours of green, renewable energy from the geysers than any other place.
This facility, north of San Francisco, owned by the Northern California Power Agency, an association of nonprofit utility companies, developed cost-effective green technologies way back in the 80s. They produce electricity 24/7 without the use of oil, coal, or uranium.
We have a capability of about 120 megawatts, which is enough to power about 120,000 homes.
This is earthquake country, remember? The geology around here is unstable, and that turns out to be a good thing. Beneath these mountains, for instance, magma, molten rock, usually found deep within the Earth's core, has bubbled up close to the surface. So close and so hot that if you put a loop of pipe in the ground and injected water into one end, a blast of steam will come out the other. Powerful enough to drive this massive electrical turbine.
The Geysers project is the largest geothermal project in the world. This geothermal power represents about 5% of the total consumption of electricity in California.
Right now we're sitting in the nerve center of Plant 1 at NCPA. We have 2 power plants. This is one of them. This plant in particular has 2 steam turbines.
At this renewable energy plant, little is wasted. Even the water injected into the earth generates electricity as it rushes past turbines placed into the down wells. And after the steam comes roaring out of the up wells and has spun these monster turbines, it condensates in these cooling towers and the water reused. A portion, though, is lost to evaporation, so more water needs to be added to the system. This is California, however, where water is a precious and costly commodity. So the engineers at the Northern California Power Agency have taken green energy to another level.
We presently are pumping roughly 9 million gallons a day of secondarily treated effluent.
That means sewage water, treated sewage water, mind you, from Lake County, providing that cash-strapped community a free and environmentally sound way of disposing of their effluents. But the wastewater is accumulated down in a valley, miles away. Pumping it so far and so high takes energy.
We pump it through 7 pumps here at the Southeast Geysers, past the B Street booster pump. From there, gravity feeds past Middletown treatment plant to Bear Canyon 1, and we pump it through 3 pump stations up here to the geysers to put it into our reinjection wells to recharge our steam field.
To power all these pumps, geothermal engineers have turned to a different source of energy, the sun, and a field of photovoltaic panels.
So what you have here are 2 renewable energy sources working in tandem to keep the most efficient, cost-effective mechanism for delivering renewable energy to our customers.
Using little more than the sun above and the earth below to power our homes far into the future.
Andrews is one of thousands of farmers in the state struggling to keep their crops green during a record drought.
And it's lifting the water.
He is turning to what he calls a last resort, drilling for groundwater.
You're looking at $200,000 to drill a well. You're looking at the pumping cost every month of about between $2,500 and $3,500 per well.
Farmers like Andrews use about 80% of the state's developed water, growing everything from tomatoes to almonds. With the drought in its 4th year, farmers are drilling deeper and deeper, running pumps day and night.
These are just running all the time but burning diesel?
Yeah, they're running all the time. They're burning 4 gallons an hour.
All that pumping has consequences. As the groundwater gets drawn up, the land sinks down. Scientists call it subsidence.
These fields in California's Central Valley have been sinking by more than 1 foot per year. That means that about 5 years ago, these fields would have been above my head.
The ocean is getting higher. You might be someone who wants to debate the cause, but there's no denying that the world's sea levels are getting higher. Since 1900, the global sea level has risen by as much as 21 centimeters, and since just 1993, it's risen by 7.5 centimeters. And many scientists expect that that rate of rise is going to accelerate across the course of the 21st century, to the point where at the end, in 2100, we might see a rise by as much as 2.7 meters from what we see Sea today. That might not seem like very much, but the results of that would be catastrophic for countries across the world, and perhaps nowhere would end up getting slammed as hard by Poseidon's wrath as the Netherlands, which is uniquely vulnerable to rising sea levels and always has been. In 325 BCE, the ancient Greek geographer Pytheas said of the Netherlands as he was passing through it that more people here died in the struggle against water than in the struggle against men. Roughly 1/3 of the land in the Netherlands is located beneath sea level, and 2/3 of her land is considered to be extremely vulnerable to flooding. And as a result, the Dutch have been fighting a war against the ocean that threatens them for centuries. And in the past, they've come up with some pretty ingenious solutions to fight against their water problem. They've constructed dikes, dams, floodgates, canals, pumping stations, and more, all in their effort to push the sea back. In 1933, the Netherlands completed construction of the Afsluitdijk Dam, which separated this historical body of water known as the Zuiderzee from the North Sea. Over time, the Zuiderzee became a freshwater lake, and the Dutch even managed to drain some of it out to reveal new lands for settlement. This new land that the Dutch managed to dig up from beneath the waves is roughly twice the size of Singapore, and is today home to over 400,000 people who now call it home. Without this complicated system that the Dutch have built over the centuries, the Netherlands would naturally look like this today, and millions of people and buildings would all be underwater. But the ocean has not entered into its final form yet, and the biggest challenge that the Netherlands may face from it is still ahead. The current system that the Dutch have built is up to the standard that a single flood can be expected in the west of the country about once every 10,000 years, and in the rest of the country that's less inhabited about once every 4,000 years. But the current system is not built according to the worst-case projections for sea level rise by the end of the 21st century. If sea levels do in fact end up rising up to 2.7 meters higher than what they are today, this is what the area around the Netherlands will end up looking like. Nearly half of the country is going to be underwater, including her most major and important cities like Amsterdam, Rotterdam, The Hague, and Utrecht. Belgium, Germany, Denmark, France, and England will all suffer significant parts of their coastlines going beneath the waves as well. So in the event that this ends up happening, only a very radical solution could push the ocean back. And what better people to come up with that radical solution than the Dutch, who have been fighting this very war for centuries? Enter the proposal made by a Dutch scientist and his German colleague, dubbed the Northern European Enclosure Dam, or NEED for short. The proposal calls for the construction of a series of colossal dams around the perimeter of the North Sea and the English Channel in order to block the rising sea levels from getting inside and threatening Northern Europe. The shorter of these sections would be built across the Channel from Cornwall in England over to Brittany in France, a distance of 161 kilometers across an average depth of roughly 85 meters. Of course, to simplify the engineering challenges and resources required, the dam could be constructed further back in the channel across the significantly more narrow Strait of Dover. But then, it'd be leaving all of the land in southern England and northern France vulnerable to the wrathful ocean's waves. The northern part of the structure would be a collection of island-hopping dams that originates in mainland Scotland and stretches from there out to the Orkney Islands, and then from there over to the Shetland Islands, and then finally from there it would stretch out 331 kilometers across the open ocean to western Norway. This final section would of course be the most challenging to accomplish from an engineering perspective, particularly because the depth across most of it is well over 100 meters. And once the dam approaches Norway, the depth dramatically increases to well beyond 300 meters in some places. To make matters even worse, the finishing point for the dam here in western Norway isn't really connected to the Norwegian mainland. It's on an island called Sotra, so another small series of dams would have to be constructed from here over to the Norwegian mainland somewhere in order to completely enclose northern Europe from the rising ocean outside. The paper's authors claim that the total cost for this entire project would be somewhere between the range of 200 billion and 500 billion euros. But they also note that that would be less than 0.1% of all the country's GDPs within the dam who would have their coastlines devastated if they chose to do nothing instead. If the NEED ever does hypothetically get built in the future, it will give the countries around the North Sea the ability to do something very interesting. they could begin to artificially control the sea level inside of the dam, which means that if they lowered it, they could begin to reveal lands that have been lost to humanity for thousands of years. As recently as just 8,000 years ago, the British Islands were actually the British Peninsula, because a huge piece of land existed where there's now only water between it and Europe. This land is known today as Doggerland, and roughly 8,000 years ago, rising sea levels flooded this low elevated land and submerged it, which separated the higher hills of Britain from the European mainland. If the need was constructed though, the countries around the North Sea could begin to drain water out and reveal as much of this ancient land as they want for modern settlement and colonization, which might actually be vitally important good land to resettle the millions of expected climate refugees from other less fortunate parts of the world on. The Netherlands could expand to become a super Netherlands who doubles, triples, or even quadruples her current land size. But the geopolitical consequences of constructing the need and draining the water inside should bear some dire mention. First of all, the absolute shock of connecting Britain with Europe via land would almost certainly deal a huge psychological blow to a lot of people. Britain's whole identity is so wrapped up into being an island and being separated from the rest of Europe. So actually being connected by a piece of land to the European Union and the European continent that people and vehicles could just move freely across back and forth that couldn't be protected or defended by the Royal Navy would certainly be a problem to a lot of people, I'm sure. I also cannot possibly imagine a scenario in which Russia would be happy that their Baltic Sea fleet and ports would be trapped within what's essentially a big bathtub. As I've said many times in many videos in the past, Russia's entire identity has been based around overcoming being effectively landlocked, and their ports on the Baltic Sea are one of their only paths to trade and naval expansion out towards the larger global ocean. If the need was constructed, it would effectively check Russian naval ambitions and block them inside of the Baltic, leaving only the Black Sea as Russia's sole year-round access into the world's oceans. So they wouldn't be happy, and neither would international trade either. If the dams were constructed without any entrances or exits, then global trade would take a massive hit. Out of the top 10 busiest cargo ports in Europe, 7 of them would all be located within the confines of the need: Rotterdam, Antwerp, Hamburg, Amsterdam, Bremerhaven, Primorsk, and Le Havre. All of these ports combined make the English Channel the single busiest shipping route anywhere in the world, and the closure of it would almost certainly crash the entire European economy. So there's gonna need to be a way to get these ships out and back in so that the spice continues to flow. Finally, there's also the minor problem of the North Sea, Channel, and Baltic gradually turning into the world's biggest freshwater sea. Water circulation from the outside ocean would be obviously restricted from entering, whereas freshwater discharge from rivers like the Rhine, the Meuse, the Thames, and dozens of others would just keep flowing in. So over time, the body of water inside of the need would gradually turn into fresh water. And who knows what kind of catastrophic environmental problems that might end up having. In short, the authors of the Need paper do not intend that the construction of the dam should be the solution to global climate change. Rather, they published it as a warning to us all of the radical solutions the world might one day require if we don't fix the problem right now in the present.